These are the answers to homework 2B. Question number 1. Identify the 3 ways to prepare a buffer. 3 ways to do that are first, combining a weak acid and a salt containing its weak conjugate base. Number 2, combining a weak acid with a lesser amount of a strong base. 3, combining a weak base with a lesser amount of a strong acid. Number 2. A solution is prepared by mixing 60.0 milliliters of a 0.10 molar acetic acid solution and 40.0 milliliters of a 0.10 molar sodium acetate solution. Will this be a buffer? This particular solution has acetic acid, which is a weak acid, and it contains the acetate ion, which is the conjugate base, the weak conjugate base of acetic acid. So because it has a weak acid in its conjugate base that's weak, we would say yes, it's a buffer. What will be the pH of the buffer? To do this, we'll use the Hasselhoff equation. And because we're mixing volumes together, we'll have to calculate the moles of each of the components. And then use the Hasselhoff equation, we'll need to have the pKa of whatever the acid is, the weak acid in the buffer. The weak acid is acetic acid. And so if we look up on handout 3, the Ka of acetic acid, which is 1.8 times 10 to the minus 5th, the pKa value we'll be using in the Hasselhoff equation are 4.74 with a guard digit 5. The number of moles of the two components are calculated by going molarities times volume. So 0.10 moles of acetic acid per liter multiplied by 0.0600 liters gives us 0.0060 moles of acetic acid. The 0.10 moles of sodium acetate per liter multiplied by 0.0400 liters gives us 0.0040 moles of sodium acetate. And when that completely dissociates, because there's one acetate in the formula, we'll have 0.0040 moles of acetate. So we now have the two components in the solution. We can now apply them to the Hasselhoff equation along with the pKa of 4.745. If we put the moles of the acetic acid on the bottom, 0.0060, and the moles of acetate on the top, 0.0040, this calculates to make a pH of 4.57. Is this an acidic or basic solution? Because the pH of this buffer is less than 7, that means this is making an acidic buffer solution. So hopefully, if you add a strong acid or strong base to this solution, the acetic acid and the acetate ions will react away any strong acid or strong base you put in there and attempt to maintain that pH as close as they can to 4.57. Number 3. A solution is prepared by mixing 60.0 milliliters of a 0.10 molar acetic acid solution and 40.0 milliliters of a 0.10 molar sodium hydroxide solution. Will this be a buffer? The two components we have in this problem are a weak acid, and then we have a lesser amount of a strong base. So whenever you have a weak acid and a lesser amount of a strong base, it will produce a buffer. Can we get the pH of the buffer? Yes, but we'll have to use the amended Hasselhoff equation because one of the components in the solution is a strong component, in this case, a strong base. So we'll need to calculate the moles of each of the components. So for the acetic acid, it was 0.10 moles per liter multiplied by its volume of 0.0600 liters. That comes out 0.0060 moles of acetic acid. We were putting in 0.10 moles of sodium hydroxide per liter, that's its molarity, multiplied by its volume of 0.0400 liters. Liters cancel out, we have 0.0040 moles of NaOH, which completely dissociates and would therefore have 0.0040 moles of hydroxide floating in the container. Because it's a strong component, in this case a strong base, we're going to write the Hasselhoff equation for a buffer that has acetic acid as the weak acid. In the log term, moles of acetic acid go in the denominator, and the numerator would have to go moles of its conjugate base, which is the acetate ion. The hydroxides then are added to or subtracted from those two values. And because bases react with acids, we're going to subtract the moles of hydroxide from the acid moles, which is in the denominator. So the denominator is going to be minus moles of hydroxide. The numerator will be plus moles of hydroxide. And now if we plug the values in, the pKa of acetic acid, we had it from earlier in the homework, 4.745. Now in the log term in the denominator, 0.0060 moles of acetic acid minus the 0.0040 moles of base. And in the numerator, there were no acetate ions. We have to add to that the moles of the base, 0.0040, and that allows us to calculate the pH of this buffer, which is 5.05. That's a pH that's less than 7, so this is also an acidic buffer. Number 4, a solution is prepared by mixing 75.0 milliliters of a 0.40 molar ammonia solution and 25.0 milliliters of a 0.60 molar ammonium chloride solution. Will this be a buffer? This is a solution that contains ammonia, which is a weak base, and then it has ammonium chloride, which has the weak conjugate acid of ammonia. So because this has a weak base and its weak conjugate acid, this solution will produce a buffer. What will be the pH of the buffer? We'll use the Hasselhoff equation to do this. We'll need to have the pKa of the acid that's in this buffer. Ammonia is a base, ammonium is the acid, and handout 3 actually has the Ka for ammonium listed. So we're going to take the negative log of that value, 5.6 times 10 to the minus 10th. And so the pKa for this buffer is going to be 9.25 with a guard digit of 2. We're mixing solutions together, so let's calculate the moles of each of the components. It was 0.40 molar of ammonia, so 0.40 moles per liter multiplied by the volume of 0.0750 liters gives us 0.030 moles of ammonia. And the molarity of the ammonium chloride was 0.60 molar, so 0.60 moles per liter multiplied by 0.0250 liters. We get 0.015 moles of ammonium chloride, and when that ionic compound completely dissociates in water, we'll get 0.015 moles of ammonium ions. Now we can plug these two numbers into the Hasselhoff equation. We know the pKa as well, 9.252. In the denominator is the moles of ammonium, which is the acid, that's the 0.015. And in the top is the moles of ammonia, which is the base, 0.030. And this calculates to make a buffer whose pH will be 9.55, which is above 7, so this is going to be a basic buffer. Number 5, a solution is prepared by mixing 75.0 milliliters of a 0.40 molar ammonia solution and 25.0 milliliters of a 0.60 molar hydrochloric acid solution. Will this be a buffer? In problem number 5, this will be a buffer because you're mixing a weak base ammonia with a lesser amount of a strong acid. That's the third way in which a buffer can be prepared. To calculate the actual pH of this buffer, we'll calculate the moles of each of the components. Again, second problem in a row, we have 0.40 molar of ammonia, 75 milliliters of it, so multiply by 0.0750 liters, and this gives us 0.030 moles of ammonia. In this case, we have 0.60 molar hydrochloric acid, so 0.60 moles per liter, multiplied by its volume of 0.0250 liters gives us 0.015 moles of HCl, which is a strong acid, so it 100% ionizes, producing 0.015 moles of hydronium ions. Now, one of the components here is a strong component. It's a strong acid, so we'll have to use the amended form of the Hasselhoff equation. So the pH will equal pKa plus the log of, it'll be the acid on the bottom, moles of NH4 positive, that's the weak acid, over moles of the weak conjugate base on the top, NH3, and then we're going to add and subtract from those the moles of the strong acid. And the way you figure it out is you ask yourself, what do acids react with? They react with bases, so the moles of the hydronium have to be subtracted from the moles of the base, which is the ammonia at the top. So in our log term, the numerator is going to be moles of ammonia minus moles of strong acid, while the denominator will be moles of ammonium plus moles of strong acid. So we had 0.030 moles of ammonia. We subtract from that the 0.015 moles of the hydronium. In the denominator, there were no ammonium ions put into the solution. That's 0. But we're going to add to that the number of moles of hydronium ions that we added. And this will allow us to calculate a pH of 9.25, which means this, because it's greater than 7, would make a buffer solution that is basic. Number 6. A solution is prepared by mixing 10.0 milliliters of a 0.25 molar hydrochloric acid solution and 40.0 milliliters of a 0.20 molar potassium chloride solution. Will this be a buffer? Here we have an acid and its conjugate base. HCl is an acid, Cl minus is a conjugate base. However, HCl is a strong acid and Cl minus is a non-conjugate base. This does not make a buffer. A buffer has to be a weak acid and its weak conjugate base, so no buffer is created here. Next says calculate the pH of the solution. To do this, let's calculate the moles of all the components in this solution. We actually took hydrochloric acid, 0.25 molar, so 0.25 moles per liter. If we multiply it by its volume, 0.0100 liters, this solution is going to wind up containing 0.0025 moles of HCl, which completely ionizes. So there's one H and one Cl in the formula, so multiply 0.0025 by 1 for each of them to get their moles. So 0.0025 moles of hydronium, 0.0025 moles of chloride. That's what comes from the HCl solution. Then we have a KCl solution. It was 0.20 molar. That means 0.20 moles of KCl per liter. Multiply by its volume. That's going to tell us how many moles of KCl will be in the solution. And because it's a soluble ionic compound and completely dissociates, we can calculate the moles of each ion just by multiplying by the number of ions in the formula by the moles. So 1 times 0.0080 gives me the moles of potassium, and 1 times 0.0080 gives me the moles of chloride. These are the ions that are in the solution. If they want to know the pH is going to come from the moles of the hydronium ions that are in your solution. There's nothing for them to react away with, so we actually have 0.0025 moles of hydronium. pH is the negative log of the hydronium ion molarity, so we've got to switch moles of hydronium into molarity, which means we have to divide it by the volume. And what were we doing in number 6? We were mixing 10 milliliters with 40 milliliters. That makes 50 milliliters, or 0.0500 liters. So if you want the pH, you have to first calculate the concentration of the hydronium ions, which is moles divided by liters. And then once you have the molarity of the hydroniums, which in this solution comes out 0.050, you take the negative log of that number. And the negative log of 0.050 will give us a pH of 1.30. The last part in question number 6 says, what will be the concentration of the chloride ions in the solution? Well, how many chloride ions do we have? Let's see, from the HCl, there were 0.0025. From the KCl, there were 0.0080. Add those together. That's going to be the total number of moles of chloride in the solution. And that comes out 0.0105 moles. Now, if that's the total moles of chloride and they want the molarity of the chloride, you have to take the number of moles and divide it by the volume of the solution, which again was 50 milliliters. So if we divide the moles of chloride by 0.0500 liters, that'll be the molarity of the chloride ions that are in the solution, and that comes out to 3 significant figures, 0.210 molar. Number 7, a buffer is prepared by mixing 20.0 milliliters of a 0.60 molar phosphoric acid solution with 10.0 milliliters of a 1.8 molar sodium dihydrogen phosphate solution. 7a, calculate the pH of the solution, and then is it acidic or basic? So this particular solution has 2 different components. We're mixing volumes together. So what I'm going to do is I'm going to calculate the moles of each of the components. The phosphoric acid is the weak acid that's going to be in this buffer. And to use the Hasselhoff equation, we're going to need to know its pKa. So from handout 3, I'm going to look up the Ka of phosphoric acid. It would actually be the Ka1 because they say phosphoric acid. That means H3PO4. So it's the Ka for the first hydrogen being removed. So that's 7.5 times 10 to the minus third. And the negative log of that turns out to be 2.12, and then 49 is guard digits. That's our pKa. To get the moles of each of the components, I'll take the molarity of the phosphoric acid, 0.60 moles per liter, multiply by its volume. Liters cancel out, and we'll have 0.012 moles of phosphoric acid. The second component in this particular solution is sodium dihydrogen phosphate. So a sodium ion is Na positive. Dihydrogen phosphate means a phosphate ion that has 2 hydrogens bonded to it. You notice phosphoric acid is H3PO4, so dihydrogen phosphate would be H2PO4, and because it's missing a positive hydrogen, it would have a charge of -1. So if sodium is +1 and H2PO4 is -1, the formula is NaH2PO4. And they're telling you it's 1.80 molar, so 1.80 moles per liter. Multiply that by the volume, liters cancel out, and that gives you how many moles of sodium dihydrogen phosphate are in the solution. And the name is sodium dihydrogen phosphate because those are the 2 ions. When it dissolves, the sodiums separate and float off. The dihydrogen phosphates separate and float off. There's only one dihydrogen phosphate in the formula, so therefore the moles of dihydrogen phosphate will be 0.018. What's the significance of that dihydrogen phosphate? That's the conjugate base of H3PO4, right? How do you get a conjugate base from an acid? You take the acid, you pull a hydrogen ion off. So when one hydrogen ion gets removed from H3PO4, it becomes its conjugate base H2PO4-. So this solution has a weak acid, H3PO4, and it has its corresponding weak conjugate base, H2PO4-. So in the Hasselhoff equation, the denominator will be the number of moles of H3PO4. The numerator will be the number of moles of H2PO4-. We know both those values, and we know the pKa of H3PO4. So we can therefore now solve for the pH of this buffer, and that comes out 2.30. Now in part B, we're going to do our first real application. We've been saying how if you have a buffer solution, if you add any strong acid or strong base to it, it maintains its pH. It does not change drastically. So we're going to do our first calculation to see if this really is the case. We have a buffer solution whose pH is 2.30. Part B says, calculate the final pH if 1.0 milliliter of a 1.0 molar hydrochloric acid solution is added to this buffer from 7A. So we're going to add some HCl to it. We would imagine the pH would go down, and if it was just added to water, the pH would go down drastically, but let's see how much the pH of this buffer goes down. So this particular buffer we have here is an acidic buffer because the pH is 2.30. Let's see what happens when we add the hydrochloric acid. Now, we're mixing two solutions together, so we need to calculate the moles of each component. And in 7A, we already calculated how many moles of phosphoric acid and how many moles of dihydrogen phosphate there were, so I'm not going to do those calculations again, but I will calculate the number of moles of HCl. It was 1.0 molar. There was 1 milliliter of it. If I multiply moles per liter by liters, I'm going to calculate how many moles of hydrochloric acid are being added to the buffer. And hydrochloric acid completely dissociates, so we're going to get or ionizes actually, so we're going to get 0.0010 moles of hydronium ions. So now our solution contains a strong acid. We need the amended form of the Hasselhoff equation. So the amended form of the Hasselhoff equation will have to include the hydronium ions, and because hydronium ions are acids, they react with bases. The numerator is going to be minus the moles of hydronium. The denominator will be plus the moles of hydronium. So if we put in our pKa, put in the denominator 0.012 moles of H3PO4, and we add to it the moles of hydronium. In the numerator, we take 0.018 moles of dihydrogen phosphate, subtract the moles of hydronium. We'll see how much the pH changes by having a whole milliliter of 1 molar HCl added to the buffer. And the pH changes from 2.30 down to 2.24, so it only goes down 0.06 of a pH unit by having a whole milliliter of fairly concentrated 1 molar hydrochloric acid added. Let's go to C. Calculate the final pH if 1.0 milliliter of sodium hydroxide is added to the buffer instead. So our buffer from A has a pH of 2.30. Let's see what happens if we add 1 milliliter of sodium hydroxide. That should actually make the pH go up. So once again, we already had calculated the moles of the phosphoric acid and the dihydrogen phosphate. I'm not going to do that again, but I will have to calculate the moles of the sodium hydroxide we're putting into the solution. So molarity times volume is going to give me moles. And because there's one hydroxide in the formula of NaOH, I go 0.0010 times 1, and the moles of hydroxide that we're putting in this buffer are 0.0010 moles. One of the components now is a strong component, in this case a strong base, so we have to use the amended form of the Hasselhoff equation. And because bases react with acids, the moles of hydroxide will be subtracted from the acid part of the logarithmic term of the Hasselhoff equation, which is the denominator. So my moles of H3PO4, we subtract moles of hydroxide. The moles of H2PO4-, we add moles of hydroxide. So the denominator 0.012 minus 0.001, the numerator 0.018 plus 0.001, and we calculate the pH. We see the pH has gone up from 2.30 up to 2.36, so it's gone up by 0.06 pH units. So it maintains that pH within at least 1/10 of a pH unit, even though we've added a significant amount of base. Number 8, a solution is prepared by dissolving 0.20 moles of formic acid and 0.020 moles of sodium formate in enough water to make 100.0 milliliters of solution. A says calculate the pH of this solution and is it acidic or basic. So this particular solution in number 8 has a weak acid, formic acid, and a salt containing its conjugate base, its weak conjugate base, the formate ion. So we can calculate the pH from the Hasselhoff equation. We'll just need to look up the Ka for formic acid. Here's formic acid's formula, and calculate its pKa by going the negative log of the Ka value, which we find on handout 3, 1.8 times 10 to the minus 4th. So that comes out 3.74, and then the 4 sevens are guard digits. Now they're telling me how many moles of each component there are. I can just then use the Hasselhoff equation with the ratio of the moles, or I could actually take the moles and divide it by the 0.1000 liters and get molarities. Either way will give me the same answer, but I'm going to do less work, so I'm just going to do the ratio of the moles. So I know my pKa value is 3.7447 plus the log of, it's going to be the moles of the formate ions on the top, 0.020, divided by the moles of the formic acid on the bottom, 0.20, and the pH of this buffer turns out to be 2.74. Now, we're going to see how much the pH changes when we do a couple of things to it. In part B, calculate the final pH if 0.10 gram of sodium hydroxide is added to a 50.0 milliliter sample of the buffer solution from A, assuming the 0.10 gram of the sodium hydroxide doesn't affect the volume. So we have a buffer solution. This one actually is an acidic buffer solution because the pH is less than 7. And so we're going to need to calculate the moles of all the species present. Now, for the sodium hydroxide, we were putting in 0.10 grams. So if you ever have mass data, the way you get moles is use the molar mass you calculate from the periodic table. So if you add up the mass of 1 mole of sodium, 1 mole of oxygen, 1 mole of hydrogen from the periodic table, you get 40.00 grams. What does that number mean? That means 40.00 grams of NaOH equals 1 mole of NaOH. And if you write that equality statement as a fraction with the 40.00 grams on the bottom and the 1 mole on the top, you're going to cancel out the grams and you'll calculate how many moles of sodium hydroxide are being added to this buffer, which is 0.0025. And when it's added, the sodium hydroxide will then dissociate completely, and so you'll have 0.0025 moles of hydroxide ions. Now, if you're going to make a mistake, here's where it happens. You had a solution that was 0.20 moles in formic acid, 0.020 moles in sodium formate. That's how many they put in there. But how much solution did they make? If you read the problem, it says they put it in enough water to make 100 milliliters of solution. Here in part B, they say you're adding 0.10 grams of sodium hydroxide to a 50 milliliter sample of the buffer. 50 milliliters is what fraction of 100 milliliters? It's half. So you're not going to have all 0.20 moles of formic acid in that 50 milliliter sample. You're only going to have half of it. So this is what you have to do. You have to realize that if my original solution that was 100 milliliters contained 0.20 moles of formic acid, and I'm only taking 50 milliliters out of the 100, well, 50 out of 100 is a half. I could have written my 1/2 as 50 over 100 if you like that better, but I'm just taking half of it. So the solution in part B is really going to contain only 0.10 moles of formic acid. And then the same thing is going to be true for the formate ions. It's not going to be 0.020 moles of formate ions here in part B because we only are using 50 milliliters out of the original 100 milliliter sample. So you have to take 1/2 of the 0.020 moles of the formate ions. Therefore, it's 0.010 moles of formate ions. So now we have the moles of all three components. And because we have a strong base as one of our components, we need the amended form of the Hasselhoff equation. And the amended form with a strong base will have the number of moles of hydroxide subtracted in the denominator. It'll be added in the numerator. So if we do this correctly, the pKa 3.7447 plus the log of the numerator should be 0.010 plus 0.0025. The denominator should be 0.10 minus 0.0025. And so therefore the pH changes to 2.85. If you left the moles of the two original components as 0.20 and 0.020, your answer is going to be close to mine, but it's not going to be correct. So as you're doing your extra homework assignments, if you don't get the exact answer I have, it could have been that you didn't account for the fact that you were only taking a sample of the original buffer solution. Let's see C. This says calculate the final pH if 1 gram of sodium hydroxide is added to a different 50 milliliter sample of the buffer. So here in part B, we added 1/10 of a gram, and it made the pH of the buffer only go up barely from 2.74 to 2.85. What do you think is going to happen if we add a whole gram of sodium hydroxide? Probably going to have a little bit bigger effect on the change of the pH. Let's try that. So 1.0 gram of sodium hydroxide needs to be converted into moles with its molar mass. That gives us 0.025 moles of NaOH, which would be 0.025 moles of hydroxide ions in the solution. And because we're taking another 50 milliliter sample of the original buffer, we're going to have half of the moles that were present in the original buffer. So when I use my moles of formic acid and moles of formate ions, I'm going to use half of each of those original numbers I gave, and then I'll put the moles of hydroxide in the adding and subtracting part of the Hasselhoff equation. So the numerator 0.010 plus 0.025, the denominator 0.10 minus 0.025, and the pH of this solution rises from 2.74 up to 3.41. So the more strong base, or it would be true for strong acid, you put into a buffer, the more the pH actually really does change.